Now, what will happen if the particles were indistinguishable, and what is the situation, what are the situation in which indistinguishable particle arise? So, as I said, that classical particles are distinguishable because each particle follows a particular trajectory. Therefore, we can detect the particle even when they are close together, because the classical particles really will not like collapse onto each other. You can still, there will be particles who, even if they come closer, you can still say this is particle 1, this is particle 2, because we have been following that particle all along. However, for quantum particle, for example bosons and fermions, they are indistinguishable. So, bosons, there are two kinds of quantum particles are there. One is called boson, which are those are indistinguishable, and they have integral spins. Another characteristics of boson is that many of the bosons can reside on the same energy level. So, photon is a boson particle, like Higgs boson people know about a lot. That is a boson, that has integral spins. Similarly, electron, protons also are indistinguishable, they are quantum particles. And the reason they are indistinguishable is that when let us say hydrogen molecule, when two electrons come close together and form bond, you can never distinguish which is electron 1 and electron 2. All that you write is a wave function associated with both the electrons together. You do not identify. So, when they are far apart, maybe hydrogen atom has electron 1, hydrogen atom number 2 has electron 2, but when they are close, then you cannot distinguish the electron anymore. So, therefore, electrons are indistinguishable particles, and they are fermions because they have half integer spins, and fermions have a speciality that not more than 2 fermion can stay in the same energy level due to Pauli's exclusion principle. So, for fermions, the energy level can have either 0, 1 or 2 particle. For bosons, however, you can have any number of particles. However, both fermion and bosons are indistinguishable particles, unlike classical one, which are distinguishable particles. So, in that case, then we have to still identify how to get the statistics, how to calculate W's, and how to get the distributions or probability distributions of the particles in different energy levels with respect to the energy. So, let us see that. So, we will see that bosons and fermions will follow different statistics, and this is called quantum statistics. It may be intimidating for you to knowing the term quantum statistics, but in this particular course we are not going to go into mathematical detail of derivations of any of those quantum statistical formula. All that we are emphasizing at this point is that these particles are indistinguishable. The rest of the things are same as what we have discussed. So, and it will not be complicated, as you can see soon. So, let us talk about bosons. Again we are going to talk about the same thing, 5 units of energy, 4 particle. Only thing, the picture will look very different now. The picture will look like this, all are blue particles. Remember the earlier ones where they had different colors. So, colors were distinguishing the particles for us basically. So, now we are putting all same color. So, therefore, we can no longer distinguish whether the green particle is up or red particle is up or which particle is up. So, how many possible ways we can get this distribution? Only one possible way, because either we bring whatever particle we bring, we do not know which particle we are bringing up, right. So, there can be only one way of getting. So, the number of microstates for distribution A is 1. Remember, however, the number of distribution still remains to be P partition of 5 units of energy into 4 particle. So, P 5 4 will be still 6. However, individual microstates of individual distribution will be just 1 instead of n factorial by n 1 factorial n 2 factorial, because this is no longer distinguishable. So, these are the 6 possible distributions that we had shown you before, but only thing is that in that particular case you had all different colors. Now, you have all same color, and because of that all the W's now are 1. You can no longer distinguish that whether which particle has gone up and which gone down. So, then automatically what we get is that we get 6 distributions and we got only 6 microstates. Remember how many we got? 56 microstates we got all total when the particles were distinguishable. Now with indistinguishable particles we only get 6 possible microstates. So number of particles in all 6 possible microstates is 4 into 6 is 24. So total there are 24 dots in this graph, and now we want to identify how many particles are there in which level. So for example, you see that level 1 has 5 particles, energy level 5 has 1 particle, energy level 4 also has only 1 particle, energy level 3 has 2 particle, this one and this one, energy level 2 has 4 particle, energy level 1 has 1, 2, 3, 4, 5, 6, 7 particle, and energy level 0 has 3 plus 2 5 plus 2 7 8 9 particles. So you see each energy level we can just count from this distribution and we can get the number of particles in each energy level. And now since we are combining all possibilities, then we have to divide this 9 by 24 to get the Ni by n. So this is the probabilities Ni by n as is shown here for each energy level. So now the same way similarly what we got for distinguishable particles, for bosons we get the same thing, we get the similar distributions for bosons also, and that is given by these numbers, and we can plot them. Before we do that, let us assume for 7 units of energy 9 particles. In this particular case also the number of distributions will be same as 15 which we had before, which is obtained from partition of 7 into 9, and here also we have similar distributions like A, B, C, D. However, here also the number of microstates for each of the distribution will be just 1 because particles are distinguishable. Note that we have not put with the dots because there is not enough space for putting 8 dots here, but this 8 denotes just 8 blue particle and this denotes just 1 blue particle. For example, here it denotes 7 blue particle, 1 blue particle, 1 blue particle. So just imagine that they are all blue. So earlier we did n factorial by n1 factorial and all that. Here we cannot do that because they are all indistinguishable, therefore they are all just 1. Now once you get that, how many microstates then? So 15 distributions, each distribution gave you 1 microstate, so W tot is just 15. So total number of particles from all possible distribution is 15 into 9 because we have only 9 particles, and 15 distributions, 15 into 9 is 135. Now we can count how many particles are there in which level. Let us start with 7. 7 has only 1 particle, so 1 particle. Now probability is 1 by 135 which is given by this number. Level 6 has 1 particle, level 5 has 2 particle as you can see from this, level 4 has 3 particle as you can see from this, and level 3 has 1 plus 2 3 plus 3 6 particle as you can see from here, level 2 has 11, level 1 has 30 and level 0 has 81. You can count that. You know, if you do not want to count, then there is an easier way to do that is when you partition 7 into 9, which I will just show you 1 or 2 example. Let us say you partition 7 into 9 which is I said which is nothing but 7. When you partition 7 into different parts, let us say I do this partition 5 1 1 1, no 5 1 1, that is the partition, which means that I have 2 particles in level 1 and I have 1 particle in 5. So by now let us say I do one more 4 3 4 2 1 1. This indicates that 1 particle having 4 energy, 1 particle having 2 energy, and 2 particles are having 1 units of energy. So sorry, so we will just change that. 4 2 1 1 is like 8, so we will just do 3 2 1 1, 3 2 1 1. So which means that 1 particle is having 3 units of energy, 1 particle is having 2 units of energy, and 2 particles having 1 units of energy, which means now if I get all the partitions and count how many 1s are there, we will get number of particles corresponding to 1 in its level. If we count how many 2s are there from all partitions, then we will get number of particles having energy 2. Like that we will get all possible values even without doing showing these particular distributions. We can use partitions to get that, and by then we can also count that how many particles are there in which level. Once we do that, we can just count them and divide by the total number of n, and we get the this probability distributions with energies. You see, this is my energy level and this is the probability. We can plot that, which we have done that. We have plotted that here for 5 units of energy and 4 bosons, 7 units of energy and 9 bosons, and 9 units of energy and 7 bosons. But the fit is not an exponential fit, unlike the distinguishable classical particles. This fit is this equation. So, what was the difference from the earlier one? If you see, the Maxwell-Boltzmann one was Ni by n was A e to the power minus beta epsilon j. So, if I write it differently, it will become A by e to the power beta epsilon j, or I can write it as, by bringing A down, I can write it as C e to the power minus beta epsilon j. You see here, or A prime I can see instead of. So, A prime is nothing but 1 by A. You see, the only difference is that there is a minus 1 in the denominator. This minus 1 was not there in case of Maxwell-Boltzmann distribution. This minus 1 came because we are talking about now indistinguishable particles, and especially bosons, because bosons do not have restrictions to be. Many bosons can reside in the same level. That is an important characteristics apart from being indistinguishable. These two characteristics, one is indistinguishability, another is many of them can reside, and that will give rise to this particular statistics. And I have fitted that with that particular line, although for 5, 4 it did not fit that well, but you see it fitted really well for 7 units of energy and 9 bosons, and also 9 units of energy and 7 bosons, and it will fit very well when you increase the number of particles. So, you see that going from distinguishable particles to indistinguishable particles, your statistics, that means how the probability of occupying a particular energy level, how it has changed from a normal exponential distributions to something like this particular distributions, which is an experimental observations that that distribution will follow this one. So, now if something follows this one, we know that they are boson particles. Whether we are able to distinguish or not, that is a secondary aspect, but if we get a statistics of particular distributions and it follows this one, then we know that okay, we are talking about bosons, we are not talking about Maxwell-Boltzmann. Now, the fact that classical particles follow Maxwell-Boltzmann indicate that they are distinguishable, but our eyes may not be able to distinguish them. We see all, like incense, let us say they look all the same color, we cannot distinguish them, but our inability to distinguish or distinguish has nothing to do with that. Whatever statistics we will get will tell us that what kind of particles we are dealing with, and that is the thing. So, now we got bosons, and again B is nothing but 1 by kBt, which has a good implications, we will talk about that later. Now, let us talk about fermions. Now, what is the speciality? Here we are talking about same blue particles, except that since they are electrons or protons and they have half integer spin, more than 2 cannot reside in the same level. So, the number of occupants in any level is 0, 1 or 2. Now, we are talking about 5 units of energy and 4 fermions. Sorry, this is fermions. So, you see, since we are talking about 5 units of energy and 4 fermions, since we are talking about 5-4 partitions, it is same as 5-4 partitions as was there for other two particles also. It will be again 6 possible distributions. However, all 6 are not right for fermions. So, can you tell me which one is not right? First one is not going to be right, because there are 3 particles in level 0, and which else is not right? Yes, that also will not be right. So, we will end up not with 6, because of that restriction we will end up with 4 distributions.
How do you get it from partitions? Let us say you have 5 units of energy and 4 particles. Now, you can partition the 5 units of energy among 4 particles in many different ways. For example, you put 5 units of energy to 1 particle, and then rest of the 3 particles get 0. Now, this according to the rules of the Pauli's exclusion principle 3 particles will be in level 0 and therefore it will be not allowed. Similarly, you can break them into 4, 1, 0, 0. That is an allowed one because there are 2 particles only in level 0, 1 particle is in level 1 and 1 particle is level 4. Now if you do 3, 2, 0, 0, that is also allowed. If you do 2, 2, 1, 0, that is also allowed. And if you do, let's say, 2, 1, 1, 1, and that is a not allowed transition because there are 3 particles in level 1. So for bosons, however, everything is allowed because there can be more than 2 particles also in one level. So therefore, for fermions, you have to first see the how many number of distributions, total number of distributions, and then from this total number of distributions, you have to subtract the distributions in which more an integer number appearing more than twice. Distributions where a particular integer appears more than twice. If you do that, then you will be able to get the number of fermions. You can try that, for example, with 9 units of particle, 9 units of energy among 6 particles, and then you can have, let's say, you can have 9 and then 5 zeros. That will not be allowed. That will not be allowed. If you say 8, 1, 0, 0, 0, 0, that is also not allowed. Then you have 7, 1, 1, 0, 0, 0, that is also not allowed. But then if you have, let's say, 5, then 2, 5 and 2, 7, 7 plus 1, 8, plus 1, 9, and 0 and 0, that is an allowed one because the total energy is 5 plus 2, 7, plus 1, 8, plus 1, 9, 6 particles, 1, 2, 3, 4, 5, 6, and no integer is appearing more than twice. So therefore, this is an allowed fermionic distribution where 9 units of energy distributed among 6 particles.
So now you see I am left with only 4 distributions, not 6, only 4 distributions. That means total number of particles in 4 distributions will be 16. Now let me count how many particles are there in which level. So for example, level 5 has 0 particle because this distribution was not allowed. So nothing can go to level 5. Level 4 has 1 particle which is coming from this distribution B. Level 3 has 2 particle coming from this and this distribution. Level 2 has 3 particle coming from this one and this one. Level 1 has 4 particle coming from this one and this one, and level 0 has 6 particle, as you can see, not coming from here, but 2 plus 2 is 4, 5 and 6. So once we get that, I divide 6 by 16, I get this number. I divide 4 by 16, I get this number. So I get now again the probability with the energy levels. Similarly, can you tell me which distribution? So again I am now dividing 7 units of energy among 9 particles, and I got the same, I wrote down the same distribution as was in bosons and Maxwell-Boltzmann distribution. Now which of them is allowed? Can you tell me? Actually none of them is allowed, because in every distribution there is one level which has more than 2 particles. For example, here 8 is more than 2, here 7 is more than 2, 7 is more than 2, 6 is more than 2, 7 is more than 2, 6 is more than 2, 5 is more than 2, of course, 6, 6, 5, 4, 5, 4, 3 and here 7. So I do not find any in which the number of particles is in every level is 2 or less. So 7 units of energy cannot be distributed in 9 particles for fermions. So for fermions, your energy level should be more than the number of particles. So, let us switch it around. Let us do it 9 units of energy in 7 particles, and you can see that there is only one possibility. You cannot change it to anything else, only one distribution, only one microstate, if you have 9 units of energy and 7 particles for fermions. Now, if I reduce one particle, 9 units of energy into 6 particle, I get these many possible distributions, 1, 2, 3, 4, 5 distributions I get. So, now for 5 distribution I have total number of, there are 6 particles. So, I have total 30 particles, and I can count that how many labels at which particle. As you can see that 6, 7, 8, 9 will have 0 particle, 5 has only 1 particle, 4 has 2 particle, 3 has 4 particle, 2 has 6 particle, and 1 has 8, and 0 has 9 particle, and corresponding probabilities are given here. So, we have plotted 5 units of energy into 4 fermions and 9 units of energy into 6 fermions, because the other 2 are not possible. 9 units of energy in 7 fermions gave us only one distribution, which is statistically not good, and 7 units of energy 9 particles did not give us anything. So, we just landed up with these 2, and we have shown you, but however, in this case the fitting is not by any of the other 2 equations, the fitting is done by this equation. So, remember for bosons it was minus, for boson it was minus, and for Maxwell distribution there was for Maxwell distribution this plus 1 or minus 1 was not there. Okay. So, these are the 3 different statistics, and again this is the same thing. Now, we compare all the 3 different statistics in the same graph. So, here we have taken 9 units of energy and 6 particles, because that is that is working out for all the 3 different ones. So, we have done that, and in this we are showing the 3 different distributions: Maxwell-Boltzmann distribution, which does not have plus 1 or minus 1, then Bose-Einstein distribution and Fermi-Dirac distribution. All the 3 are shown here. Sorry, I think this is plus and this is minus, this is minus, and you see that they look more or less similar. However, they are not exactly same, especially when you really increase the number of particles and energy levels, then they will differ. You can see when the energy level is higher, then of course they will follow the similar trend, and when your temperature will become higher, then also they will follow a similar trend. That is what it means. However, when the energy level is low or the temperature is low, then the Bose-Einstein Fermi-Dirac statistics or Maxwell-Boltzmann distributions, they are all going to differ. As you can see, the difference is prominent in this intermediate region. Here we have not used any formula, we have only used our own ways of distributing the distinguishable indistinguishable particles having some fixed amount of energy, and we landed up with some numbers for every given energy level, and from there we got the statistics, and that is what we have plotted, and we have shown that how this is changing with different energy levels, and that the fact that they are different for these 3 different types of particles that we discussed. Okay.